Okay guys, so this is entropy. This is quite a big one and it is quite difficult to get your head around. It's probably something you've never come across before, so you really just have to kind of think, accept what I'm saying some of the time. Think about what I'm saying, but just kind of accept that what I'm saying is true in certain cases, and then a later date think about it and think, well, why is that true? Okay? So entropy is basically a measure of disorder, of randomness. So the more random or disordered or messed up something is, the more entropy it has. So if I was to look at pictures of a solid, a liquid and a gas, we can quite easily see that the solid is the most ordered one. With these nice straight rows, nice not very random structure. So solids have quite a low entropy in general. Whereas liquid, you can see that's a little bit more messy, a little bit more disordered, slightly more random. So if I have a liquid of the same material, it will have more entropy than the solid of the same material. And to take it to the extremes, if we evaporate it into a gas, gases are very disordered, they're scattered around all over the place, moving around, doing God knows what, having a party, so they have a very, very high entropy. So low, medium, high. Your gases always have the highest entropy. What this means is, close your door please. What this means is, as you heat something up, it gets more entropy. If I want to give something more entropy, all I need to do is raise the temperature. Okay? So a couple of analogies now. If I take a solid egg, just an egg, and I throw it on the floor, will it break into a disordered mess? Yes. So all that due to the entropy, that will increase the entropy. Okay? If I scoop up that disordered mess and I throw that on the floor, will it change back into an egg? No. So that hasn't been a negative entropy change. If I take a big, nice, neat pile of bricks and I chuck them on the floor really hard, will they break into a random mess of bricks? Yes. So what's happened to the entropy? It's increased. But if I take a random mess of bricks and I throw them on the floor, will they stack up into a nice, neat line? No. So entropy has not decreased. Okay, one more kind of analogy. If I have two rows of marbles, black on the bottom and white on the top, in a box, and I shake the box, will the marbles jumble up into a different order, a random mess? Yes. So the entropy has increased. But if I take a random mess of marbles and I shake the box, will it shake into a row of black marbles and a row of white marbles? No. So entropy has not decreased. So what we find out is, over time, as we do reactions and as the universe gets older, entropy always increases. And that's just a fundamental fact of the universe. The entropy of the universe is always increasing. So 10 years ago, the universe was a much more ordered place than it is today. In 10 years' time, the universe would be a much more random, disordered place than what it is today. So the entropy is always increasing. If you do a chemical reaction, no matter where you are, you could be on Zargon 5 or whatever, no matter what you're doing, you are always increasing the entropy of the universe. If you wasn't, then that reaction wouldn't happen, so you couldn't be. Okay? So that brings us to something called the second law of thermodynamics, really important. It's in at number 2, which says spontaneous processes are those which increase the entropy of the universe. So if I want something to just happen, spontaneous, that's what spontaneous means, it just happens, then it has to increase the entropy of the universe. And we can use this to predict whether a reaction will happen. So say like, I think something's going on inside the sun, obviously I'm not going to get my little, I don't know, Humvee or my little bike and go and pedal off to the sun, am I? So I have no way of actually knowing it. So what we can do is we can figure out whether my reaction increases the entropy of the universe, and if it does, then I know it's possible. If it doesn't, I know there's no chance it could possibly happen. Because in order to be spontaneous, it must increase the entropy of the universe. So what we can do, and a kind of question you'll have to do, is you'll have to calculate the entropy change for a reaction. The symbol for entropy change is delta S. Delta means change in, S means entropy. The delta S is change in entropy. And the units of entropy, which you'll almost certainly be given in any exam, is joules per Kelvin per mole. Okay? Don't worry too much about what these mean, just be aware that this is joules, because later on you may need to change this into kilojoules depending on the question. So just be aware they usually give you in joules. Okay? So they'll give you some kind of reaction, like this first one here or this second one here, and they'll say calculate delta S for the reaction. Well, all we need to do is calculate the entropy of my products and subtract the entropy of my reactants. So using the table, which you will get given in an exam, I can see the entropy of N2O4 is 304, and the entropy of NO is 211, but I've got 2 moles of it, so that's 422, and the entropy of O2 is 205. So sticking all that in a calculator, I would get minus 324 joules per Kelvin per mole. So this reaction is actually making the universe more ordered, and that would suggest to me that it's not going to happen. This would not happen spontaneously. However, there is another factor which we're going to talk about in a bit. I won't mention it now, but just be aware there is another factor which is coming up, so this isn't the whole story. Just because the delta S is negative doesn't necessarily mean the reaction won't happen, although it's a good indication. Okay, and we'll speak about that in a minute. Just to go through my second example, I've got my 6 carbon dioxides, so that's going to be 6 times 214, and I'm going to add to that my 3 H2Os, which is 3 times 70. That is my products. I'm going to subtract from that my reactants, which is 173 for this, add 7.5 times 205, because that is the entropy of O2. Okay, obviously this is in a certain state. If you change the state, as we said, you will change the entropy. So a solid O2 or liquid O2 will have less entropy than a gaseous O2. But they'll always give you the state symbol, so that should be okay. Popping that to my calculator, I get minus 216.5 joules per Kelvin per mole. So again, that is a negative entropy change to this reaction. That suggests that this would not happen. Okay, but like I say, that's not part of the story. Okay, so what's the other half of the story? We've said that entropy will have an effect, but there's something else which can affect it too, and that is this thing called enthalpy. So let's look at an example reaction. Okay, so we already said this had a negative entropy change, so you'd expect it not to happen. But this is combustion, and we know things burn. This is hexene, so we know hexene will burn with oxygen, yet we've got this negative entropy change. So why does it actually happen? And the reason it happens is we're only thinking so far about our chemicals, what we call the system, but that's not the only story. Okay, you can think of any reaction as consisting of 2 things, the system, which is the chemicals, and also the surroundings, the thing around it, which is the rest of the universe. So if I was burning some logs in a forest, I can think of the logs as my system and the rest of the universe as the surroundings. If I had 2 chemicals reacting in a beaker, my chemicals are my system, the rest of the universe is my surroundings. Yeah, even 2 gases reacting in a room, your gases are your system, your chemicals, and everything else is the surroundings, the rest of the universe. So always think of it as like a dot in a box, these 2 things. Okay, I'm going to ask you a question. When things react, they either take in or they give out enthalpy, energy, heat energy usually. So it's either exo or endothermic. Let's, just as an example, let's say we have an exothermic reaction. What will that heat release do to the entropy of my surroundings? It'll increase it, won't it? Because it's going to make them more into a liquid or a gas, and that increases the entropy. If I had an endothermic reaction, so a positive enthalpy change for my chemicals, then it would change the gas into more of a liquid or liquid into more of a solid. So it would cool things down, and that would mean the entropy of my surroundings decreases. So really we have to think about two things. Not only do we have to think about the entropy change of my system, my chemicals, we also have to think about the enthalpy change of my system, my chemicals. Because this entropy change, this enthalpy change of my chemicals will affect the entropy of the rest of the universe. And if I want to figure out the entropy change for the universe, I need to think about both my chemical, my system, and my surroundings. Okay? So basically, a dude called Gibbs, who had possibly the most intimidating beat of all time, came up with an equation. Delta G, change in Gibbs free energy, named after himself, is equal to the change in enthalpy of your system, your chemicals, minus the temperature that you want to do the reaction at, times the change in entropy of your chemicals. Now, it turns out, if delta G is negative, your reaction will happen spontaneously, and the entropy of the universe as a whole will have increased. So we can tell whether any reaction anywhere ever will happen just by this equation. This is like why all chemistry happens. Everything is because of this. If you have a negative delta G, it will happen spontaneously. If you have a positive delta G, it will never ever happen spontaneously. No matter what you're doing or where you're doing it, it's all down to this. That's how important this equation is. Okay, so I'm going to put a question up, and we'll go through kind of an example of how you answer one of these questions. So, a Hansen chemist wanted to know whether a reaction was possible at 298 Kelvin. Now, I've given this temperature in Kelvin. Quite often they'll give it in degrees C. When we do delta G equals delta H minus T delta S, this temperature has to be in Kelvin for you to get the right answer. If you do it in degrees C, you'll get it wrong. That's a common mistake people make. 0 degrees C equals 273 Kelvin. So if you want to change your degrees C into Kelvin, just add 273. If you wanted to change Kelvin to degrees C, you subtract 273. Simple as that. So, this is already in Kelvin, so that's a good start, that's not so bad. He, whoever he is, found that enthalpy change of the system was positive 2,499 kilojoules per mole. And the entropy change of the system was plus 16 joules per Kelvin per mole. How would the muscle-bound hunk solve his problem? Well, what I do is, all you do is you feed in the numbers into this equation. So my entropy change, my enthalpy change, is positive 2,499. My temperature in Kelvin is 298. Now, a mistake a lot of people will make now is they'll say the entropy change is 16. But it's not, because this is in joules, we need it to be in kilojoules. So I'm going to do 0.016 kilojoules. Pop all this into a calculator and you should get positive 2,494.232. So this is a positive Gibbs free energy. This will not happen. Okay, this reaction cannot ever happen, even though the entropy change of your chemicals was positive, because we haven't taken into account the surroundings here when we did that. Okay, and that is entropy. Sorry about all the interruptions.